Okay, so let's go ahead and get started. Um, Today's class is mainly about what an FSM is. FSM stands for finite state machine. I mean, there are a few things I want to go over before we get to that. As you can see up here, there's some code I want to review that's part of a circuit that can divide the clock signal. And I put a handout with the code on each of the tables. It should be enough for each person. And then I want to talk about what a counter is. Well, both these things, both the divide by circuit and also the counter, even though they're not part of, well, I take that back. There is a clock divide that's part of Lab 6 that Dr. Mealy wrote that we give to you. But then you may need a clock divider like the one I'm going to show you when you do your final project, your team project. I mean, it depends what project you choose. Okay, but that's a common thing that comes up with the final project is that you need to divide the clock signal. And then also counters are common in final team projects. Like if you do a stopwatch or some type of, digital clock of some sort, counters are involved with that. So I'm going to go over an example that you do in CP 233. And then also the FSM, once we know what an FSM is, I'll also show you an example of a counter that you can make with an FSM. Okay, so that's sort of the game plan. I just want to remind everybody that tomorrow, that's when Lab 4 is due. Okay, so after we're done here, and there is an activity today. So after we're done with the lecture and you're done with the activity, if you're still working on Lab 4, that's what you should work on once we're done up here. And then Lab 5, which you have enough information, because remember, Lab 5 is basically Lab 4 with memory, along with the time multiplexer that we provide, or Dr. Mealy provides. And again, that's due a week from tomorrow. And then there's one more lab, before the final project, and that's due right before the Thanksgiving break. Okay, the 17th, that's the Friday right before the break. You don't have enough information yet to do Lab 6. Lab 6 does involve an FSM. So, some of what I talked about today, you need for Lab 6. But there's some other information that you need that you'll get Tuesday of next week. So after Tuesday's class, someone can theoretically finish all the labs. Okay. All right. So like I said, let's start with this clock divider. And on each table, you should have a handout that shows this code. So if you want to find the handout and look at it as we talk about it. So there's some things on this handout that you haven't seen before. Okay, now this would be the high-level black box diagram of a clock divider. It just has one input, one output. And the input is often called clock. And here, our input is a clock signal, a periodic square wave of 100 megahertz. And I talked about this 100 megahertz square wave last class. Like, what's the significance of 100 megahertz in this class?
It's just phase and base.
Right, exactly. This is the clock speed that's on the basis 3 board. And that's what we're feeding into this clock divider. And then the output you can see is S clock, which stands for slow clock. Okay, because what this module is going to do is take this 100 megahertz clock signal and make it a lower frequency. Okay, when we take a signal of some frequency and convert it into a lower frequency signal, we say that we're dividing it. Okay. Now, one thing you haven't seen before in the System Verilog code is right at the very top, after the name of the module clock divider, there's this number sign, and then in parentheses, parameter max count, and then you can see it's set to 1. That's a way that you can declare a variable. A parameter is just like another word for variable in System Verilog. Okay, so we're just declaring this variable max count, and we're setting it to 1. Okay. And then you can see we're declaring our input and output. You can see it's output logic because the output slow clock is within an always FF. So, you've seen that before. You might have not seen this before, that after the output logic, in S clock, we're initializing S clock to 0. So see, that's a way that you can initialize an output to 0. It's right there where you declare it. Okay. All right, and then you can see we have this count that we're declaring as logic. And how many bits is that? 30 bits, right? Because it's 29 to 0, so a total of 30 bits. And you can see that we're also initializing that count to 0. Okay, then comes the always FF block. Now, before we get to that, you should be able to tell me what range and numbers that you can represent with this 30 bits that the count is consistent.
0 to 2 to the 30 times 1.
Okay, so everybody agree with that? Now, you know, we're treating it as an unsigned number.
Yeah, assigned would be -2 to the 49 to negative the positive 2 to the 29 minus 1.
Right, because you got to subtract them. Yeah, very good, very good. But yeah, here, since we're just going to use count as an integer, we're just taking it as unsigned. So it would be 0, of course, the lowest of unsigned, up to what did you say again? It was 2 to the
30 minus 1.
2 to the 30 minus 1. And actually, I calculated what that number was. Somewhere here. Yeah, 2 to the 30. Like 2 to the 30 is 1,073,741,824. Right? So subtract 1 from that, so it'd be 1,073,741,823. Okay, but the point being is it's a big number. Okay, but you know, whatever we're going to count to, we got to make sure that we have enough bits. So you always have to look at, you know, for the number of bits that you have, you know, what range you can represent with those bits. Okay. And I just said this a moment ago that we're initializing count to what? 0, 0. Okay. All right. So now for this example, I'm going to go over, let's say that we make max count equal to 50 million. Now, one way to make max count equal to 50 million is we could just change it right here, right? Change this 1 to 50 million. But one advantage of using a parameter, or at least sometimes it's an advantage, is that instead of changing the parameter right in the code where it's initially defined, like it is in this module, you can change it in your structural model, okay? Like instead of changing it here, in your structural model, when you're connecting this up to other modules, in the line for that module, and I believe you put it between the file name and the label, you could just put $50 million, and that would change it there. Okay, so that way you can leave this as just like general and do any kind of specific changes in your top module. So sometimes that's an advantage, because let's say you have like 5 clock divides in the same project and you're not using the same max count for all of them. You know, maybe one of them you're using 50 million, another one using 25 million, you know, you're using different max counts. Well, instead of having 5 different clock dividers where the only thing that's different is what you set the max count in the code, is you can just set the new max counts in the structural model, okay, and it makes it easier. Okay, so that's why sometimes it's good to know about the parameter feature in System Verilog. Okay. Okay, but let's see how this module is dividing, picking the frequency and dividing. In other words, just making that input frequency a smaller frequency. And again, we're going to use this example of max count equal to 50 million. So we have this clock signal that's coming into our clock divider module at 100 megahertz. And what did we say the period was?
1 nanosecond.
How many nanoseconds?
1.
Not 1. 10. Yes, 10 nanoseconds. Right. Again, that's why in the sim file, right, when you're running your test cases, you put number sign 10, right, for each of the test cases. So that's delaying each test case by 10 nanoseconds, which is one clock pulse, one clock cycle. Okay? Okay, so now let's look at this code here. So we're setting count to 0, and then we have within the always FF. Now notice that the always FF in the parentheses, it has positive edge clock. So what does that mean?
On the positive edge triggers.
Right, that's how it's modeling a rising edge, that every time the clock transitions from a 0 to a 1, inside whatever's inside the always FF, that's when it's going to get evaluated. All right, so you see, we're going to evaluate the always FF on every positive edge of the clock. And you know, this just is going on forever. Okay. All right, so then within the always FF, in between the begin and the end, you can see that the first thing we do is we just add 1 to count, right? So it's initially 0, we add 1 to it, becomes 1. And now we evaluate, well, is count equal to max count? Right? And again, we're making max count equal to 50 million. So obviously, for this first edge of the clock, count is 1. It's not equal to 50 million, right? So it's just going to go back up and get evaluated again at the next clock edge, right? So now count's going to be 2. It gets evaluated against 50 million. Well, they're not equal. So can you see that this is going to keep going on, right? That oh, and also S clock was set to 1, set to 0 up here. So I forgot to write that down. But, you know, S0, its initial value is 0, right? Because we initialized it up at the top. So can you see that for 50 million clock cycles, S clock is just going to stay 0 because count doesn't equal count max count yet. It's not until count gets to 50 million, right? Which means 50 million clock cycles, and each clock cycle is 10 nanoseconds. I'll take away the so 50 million clock cycles, and each clock cycle is 10 nanoseconds. So if you take 50 million times 10 nanoseconds, what are you going to get? What's it going to equal? 10 to the 6 times 10 to the minus 9 is what?
Half a second.
50 milliseconds? 500, right? Because we got 50 times 10. So 500 milliseconds, right? Because 10 to the 6 times 10 to the minus 3 gives you 10, or 10 to the minus 9 gives you 10 to the minus 3, which is milli. So you see, S clock is going to stay low for 500 milliseconds, and then finally count's going to equal max count. And when count equals max count, now we do what's in the begin end here, where we initialize count back to 0, and then we invert S clock. See, S clock equals tilde S clock, right? So it inverts it. So after 500 milliseconds, S clock's going to become a 1, and then it's just going to do it again, right? It's going to stay 1 for 50 million clock cycles. So it's going to stay a 1 for 500 milliseconds before it goes back to 0, and then it just keeps repeating. Okay, so we've got this 100 megahertz signal coming in. If we make max count equal to 50 million, well, coming out, S clock, the slow clock, it's low for 500 milliseconds. What's 500 milliseconds in seconds?
Half a second.
Yeah, half a second. And it's going to go high for a half a second, and then low for half a second. High, you know, it just keeps repeating. So what's the period
1 second.
of S clock? Yeah, the period of S clock is 1 second. So what's the frequency?
1 hertz.
1 hertz. Right. So if you were to use this code, you know, for one of your projects, you know, and you run it on your basis board, well, the basis board clock of 100 megahertz is going to be coming in, and at the output of this module, you're going to have a 1 hertz signal. And you can get any slower frequency out of this module by just picking the correct max count, right? Because if I change the max count, I'm going to change how long what's coming out of this module is low, right? And how long it's high. So I can figure out, I can figure out the number I need in order to get whatever frequency I want. Okay. So like I said, the main reason I went over this, I guess there's two reasons. One reason is in lab 6, there is a need for a clock divider. Now we give you that clock divider. Okay, Dr. Milley actually wrote it in a different language and we give you that. But it's quite often that for team projects, your final team project, that a clock divider is needed. Okay, so you may need something like this. Okay. All right, so any questions up to this point? Everybody okay? This makes sense? Okay, so the next thing is to talk about what a counter is. And counters are also popular in team projects. If you do some sort of stopwatch, or you do any sort of clock or anything like that, or if you just want to count things, like say you're doing a game and you want to count the number of points somebody is accumulating, that's another. So anyway, counters are fairly popular. And there's also a counter in CP233. So I put the this diagram again that you've seen before of the microprocessor that you build in CP233. And if you take a look at this diagram, over on the left side towards the bottom corner, there's this module labeled PC. That stands for program counter. Okay, so it's a counter that you're going to model in CP233. And what a counter is that it's basically a register with the addition of an increment in your output. Okay, so if we just take a look at the counter itself, so I just redrew what's on that diagram up at the board here. It's got these names of inputs and outputs that you haven't seen before, but they're really what you have seen before. They're just named different. You see this PC out, that's just the Q out of a counter. And you see this PC in, that's just the D input of a counter. And you see PC underscore RST, that's reset. So, that's reset just like we've seen before with the register. Now, PCWR, WR stands for write. And write is the same thing as load, enable, enter. It's also the same as store, all those things. But you can just think of it as an enable. You can just think of this as an enable. That when it's asserted, and this is active high, so when we make this PC write high, that's when Q is going to be assigned to whatever the D input is. So it works just like an enable. Okay, so when you build this in CP233, there's basically 2 steps. First, you just model the register. I mean, the same exact code that you're going to use to make the 4-bit register for lab 5, that's the code that you would need for this program counter. Because again, it's just like a register. The only difference is, see up here, we got this block that has a +4. Well, that's the increment. That's how much we're incrementing the output every clock cycle. So, provided that we reset it at t = 0, which is typically done, your PCL is going to start at binary 0. Now it's going to be 32 bits, but it's going to be 32 zeros. So it's a 32-bit binary number, all zeros, 0. And then after every clock cycle, so every positive edge, because these are rising edge triggered in this register, it's going to take whatever the PC out is and increment it by 4 and then feed that back in. So every clock cycle, this PC out is incrementing by 4. It starts at 0, then it goes 4, 8, 12, 16, and so on. Now, when you take the class, you'll learn why it increments by 4, okay? But the key point here, again, is that a counter is just basically a register with some sort of increment to the output. And the way you would model this +4 in System Verilog is you would just use an assign statement. You would just assign this side of it, which I label T2. Now, when you take that class, you're going to use more descriptive internal signal names than I'm using here, okay? At least if you're smart, you will, because you'll have like 50 internal signals in that microprocessor, and you don't want like T2, T3 up to T50, because again, when you go to troubleshoot, you look at a timing diagram, you're gonna drive yourself crazy, because you'll be like, where's T2? So, use more descriptive names, but I'm just being very basic here. But you just assign this internal signal to this internal signal +1, or +4, excuse me. Like in that class, we're not going to have you, use an RCA, and use an RCA of some sort to do the addition. In that class, you're letting the software do the work, because Vivado will see this plus sign, and plus in Verilog does mean add. Okay, that's why we don't use it for or Boolean expressions, because we use it for add. But then the software will come up with the adding circuit that's needed to do that addition. Okay, one last thing, and I'll answer your question. So again, the thing to take from this, a counter is a register with the addition of an increment in the output. And when you go to model a counter, it's same as a register. It's just you're going to have to add something. Here it was an assign statement to get the increment. Now, I'm going to show you an example of an FSM counter that does a sequence. Okay, that's a little bit more complicated counter, but that's what FSMs are good for. FSMs are really like the holy grail of modeling digital circuits, because as you'll see, it's a combination of all the things that we've been talking about thus far. But you had a question.
You say register, you mean like memory?
Yeah, exactly. Yeah, because next class we will talk about a register called a shift register, okay, which is a little different. So yeah, but typically if someone just says register, yeah, they're talking about a memory register.
This works not memorize every can add one.
Well, adds 4, but yeah, remember, a counter is a sequential device that has memory. So in order to keep incrementing, right, it has to know the count before, so it gets the correct count after. Yeah, it's that old, you have to know where you're at in order to know where you're going, right? To know where you're at, you have to remember. Yeah, so yeah, and that's why notice it's a feedback type of system, right? See how the +4 is in the feedback output between you, which you need for anything with memory. Okay, so any questions up to this point? Because now we're going to talk about a finite state machine. Okay, and let me move the camera. So your lab 6 and your final projects, both the individual and the team final project, all involve an FSM. Okay, this is what we were working towards the whole quarter. I don't think I have it. I gotta tweak it. Okay. Now, like I just said, an FSM is part of Lab 6. It's also going to be part of both parts of the final project. Okay, so you got to have an FSM for your team project, and also the individual FSM or individual line of project contains an FSM. And then if you look at your CPE 233 microprocessor, do you see what's in the upper right-hand corner? What's that module?
We've done FSM.
Yep, CU stands for control unit, and then FSM, finite state machine. Remember, it was probably a couple of weeks ago, but we talked about what's directly below it, the CU, DC, DR, what's that? Right, decoder. And, decoders, are they sequential?
No.
They're combinational. How can you tell if a module is sequential? Exactly. Remember, if a module is sequential, it's gonna have a clock input. You see how the CU FSM has that little triangle symbol. Now, it doesn't have a line for the input, but it's understood that that's an input. Okay, where the decoder does not, right? Decoder does not have a clock input. So if you ever ask, like when you take CP 233, one of the professors, whatever professor you have, they're probably gonna ask you that like on the first day. They'll probably give you this and say, okay, tell me which modules are sequential and which ones aren't. You just gotta look which ones have the clock input, right? They're sequential, they don't, it's combination. And remember, we talked about the decoder, how instruction bits were coming into it, that's the IR, okay, and then brackets is, you know, the numbered bits coming in. And then the outputs were going to what of the decoder? Those outputs, ALU fun, ALU source A, and all those, where were they going to? Do you remember we talked about it? You look at the diagram, you see where they're going. Yeah, they're going to all the muxes, and specifically what input of the mux? Select. All right, so you see the decoder based on instruction bits, and you're gonna learn all about the different instructions for this microprocessor when you take the class. But it's controlling which input of the muxes is being used for a particular instruction. So it determines how the data is being routed through the rest of the circuit. Okay. Now, if you look at the FSM, it also has some instruction bits coming in. In fact, in some cases, it's the same instruction bits as the decoder. You know, bits 6 through 0 are going to both the FSM and the decoder, and I think that's all that goes into the FSM. Oh no, then there's also bits 14 through 12 are going to the FSM. Now look at the output of the FSM. See those outputs on the right side?
Yeah.
There's a PC write. That's this right here. So that's like an enable. There's a reg write. There's a mem WE2 where WE means write enable. And then there's some RD that stands for read. Okay, and when you take that class, you'll learn that read is when you're getting information, write is when you're putting information, you know, into say a register or something like that. But the key point I wanted to make here is that the FSM is controlling when data is read and when it's written. Okay, so the decoder is controlling the route of the data, and then the FSM is controlling like how the data is being used. Either it's being read or it's being written, which is the same thing as like, you know, being stored. And you'll learn in that class that reading information and writing information, it's time critical. Like it has to happen at certain instances. Otherwise, your microprocessor is not going to work. Routing the data, as long as you do it within one clock cycle, it'll work. Okay, it's not as time critical. Okay, so that's why the decoder is taking care of the routing of the data, but the FSM is controlling the time critical stuff. Okay, the reading and writing. Okay, so I just wanted to point that out because you know, FSMs are often used in that way when there's something that's time critical.
We saw if it writes, then it's storing in memory.
Say that again, please. Well, it's storing it someplace. Like it could be memory, it could be an output device. Yeah.
Yeah, if it's read, then it's what?
It's getting the information from memory or like an input device.
Okay.
Yeah. So yeah, it's just the direction of the data, which way it's going. You're either getting it or you're putting it out. Yeah, again, you'll learn all about that stuff next class, but I just wanted to take a few moments just to kind of drive home that a lot of what you learn in this class, you know, again, you're going to be using in that class. Okay, so let's talk about an FSM. So this is a general high-level black box diagram of an FSM. And you can see it has 3 modules. This module here is called a next state decoder. Here are state registers. And here's an output decoder. So right away, you should be able to tell me which module or which modules are combinational and which ones are sequential.
So state registers.
Yeah, because it's got a clock, right? So this is sequential. And you know, registers kind of gives it away, right? Even if you didn't see the clock. And then these decoders. Combination. So can you see why we didn't talk about FSMs like the beginning of the quarter? Right? Because they contain both combinational and sequential circuits. So before you can really understand an FSM, you have to have had, you know, experience with combinational and sequential. All right, well, state registers, they have, you know, stored information. And really, the purpose here is to know where we're at. So, you know, in a sequence of events, where we're currently at. So, you know, current event. Where are now? So state registers, they have like where in a sequence we're presently at. Okay. The next state decoder, as the name implies, it determines where we're going. Determines next states. You know, so the next state is where we're going. Right? So, you know, like concept wise, big picture wise, this has where we're at. This determines where we're going. Okay, and then you have an output decoder, and as the name implies, the output decoder just determines the output. Now, there's 2 types of FSMs. Okay, and what distinguishes the 2 is how the output is determined. Okay, so it all has to do with the output decoder and how the outputs of the output decoder are determined. That's what distinguishes between the 2 FSMs. Okay, one FSM is called a Moore. Oops. And the other one's called a Mealy. And as far as I know, there's no relation to Dr. These are both people's last names. The Moore, that's a different Moore's too. Well, I don't know if that's exactly, but I think it is, because I think Moore's law came after this.
There's more Moores.
What's that?
There's more Moores.
Yeah, I think there's more than one Moore. Positive though. Maybe it is the same person. I don't know. But anyway, getting to this, a Moore FSM, the output is only determined by the state you're in. And a Mealy, the output is determined by the state you're in and external input or inputs. It can be plural or singular. Okay, that's why you notice in the diagram, I have everything in black except these 2 red lines. If you just look at this diagram and you don't include the red lines, that's a Moore. Okay, so, you know, in the diagram, the Moore would have no red lines. If you do include the red lines, like everything you see here, what's in black and also red, that's a mealy. Okay, so the mealy, you do include the red. And so if you look here, right at the output decoder, if you have a mealy, there's no red lines. So the only thing coming into the output decoder for more are the outputs of the state register, which is the information of where you're at. Okay, so it's like your present state. So the output, the more output only depends on your present state. Okay. But if you have a mealy, the output of the mealy depends not only on the current state, but also on external inputs. It can be one or more. Okay, so that's the difference between the two. Now we'll get into like what the difference is when you build them. Okay, but that's the fundamental difference. Now, Dr. Benson has like a catchy phrase way of remembering the differences. Like her phrase is that more has less, because the more only depends on the state, or the mealy depends on the state and the external input. So I don't know if that helps. Yeah, more has less. That's how she remembers. Kind of clever, right? Because it's very concise and gets to the point. Okay, so like I said, this is like the basic information about an FSM. I mean, again, the key thing is FSM contains both sequential and combinational circuitry, and this is like high level, what's happening. Okay, now we're going to get into specifics, where through an example, I want to show you how you would go about building building an FSM. Okay, that's going to do something useful. Okay, so I'm going to use a counter example. Okay, so this is going to be an FSM counter example. And you see this counter, it's going to count in the following sequence. It's going to go 2, 0, 7, 5, 3, and then just keep repeating 2, 0, 7, 5, 3, 2, 0, 7, 5, 3. Okay. So anytime that you go to build any sort of FSM, you start with the state diagram. Okay, you always have to start with the state diagram. So let me get my state diagram here. Here we go. And every state diagram needs to have a legend. Okay, so first thing is your legend's always going to have a circle. And that circle represents a state. Okay. Also, your state diagram, inside the circle, you typically on the top put a label. And that can be, anything you want it to be. And then in the bottom half of the circle, this is where you put any more outputs. And so, whether you have 1, 2, or however many more outputs you have, you would put in the bottom half of that circle. Okay. Now, also in the legend, have this arrow. Okay. That arrow represents a clock transition. And it can either be rising as you're falling. And then if you have an external signal, you would put it right next to that arrow. Right? So this is external input or inputs. It can be singular or plural. And then below any external inputs, you would put mealy outputs. And so you know, depending on the design, like sometimes you just have more outputs. Sometimes you just have mealy outputs. And if you have mealy outputs, you gotta have at least one external input. Sometimes you have both. You can have an FSM that both has more outputs and mealy outputs. So it's like a combination of the two. Okay. All right. So anyway, that's, you know, this is called a legend. Actually, let me put it down. That's a legend. So all state diagrams, you need to have a legend. All right. So now let's make our state diagram for this counter. So each count, right, 2, 0, 7, 5, 3, I'm going to make that a state. So I'm going to have 5 circles, right, because a circle represents a state. And it doesn't matter how you arrange these circles. I'll actually make it a little bit bigger. I'll put them like a shape here. Something like this. Okay. And I'm just going to label these states by letters. See, I think I just, yeah, I used STA for state A, STB for state B, STC, STB, ST. Okay, now I'm going to start off with just having a more output that represents these numbers in my count. And I'm going to represent these as binary. Now, I don't have to. I mean, I could if I wanted to. I could represent them as a base 10 number. I mean, it's up to the person making the state diagram. You know, state diagrams are for the person that's going to design the FSM in Verilog. Because what you're going to see is once you have a state diagram, it's pretty cookbook getting the code you need in Verilog to, you know, build that FSM for that state diagram. Okay, but the state diagram is there for your use. So, you know, I'm showing you like the most common way of doing a legend and doing a state diagram, but really there is flexibility. Whatever works for you, you can make modifications to it. You know, some other notation is more advantageous. Now, what's not up for debate or up for changing is, you know, more outputs always go within the circle and mealy outputs always go outside the circle. That you can't change. You know, usually we'll put the external inputs right near the mealy outputs. Okay, so anyway, since I'm going to use binary to represent those count numbers, you know, here in my legend, you know, I'll put B2, B1, B0, right? Because I need 3 bits because I want a count of 7. Okay, so state A, I'm going to start with state A. So when we're in state A, the output of my counter is going to be a 2. So in binary, right, 2 is 0, 1, 0. Okay, then I got 0 for state B. Okay, so that's just going to be 3 zeros. State C, 3 1s, that's a 7. State D, 0, 1, that's a 5. State E, 0, 1. Okay. All right, so now to transition from one state to the other, that happens on a clock pulse. That happens on a clock edge. Okay, so you see, I'm going to go from state A to state B. So you see that represents a clock transition, like we said over here, right? Remember that arrow represents a clock transition. So if it's rising edge, it's representing a 0 to 1 transition, right? If it's falling edge, it's representing a 1 to 0 transition. Okay, so I'm just going in the order of my sequence. I'm going to go from 2 to 0, so state A to state B. And then when I'm in state B, I'm going to go to state C. Right, state C, I go to state D. State D, I go to state E. And then because it repeats, right, state E, I go back to state A. Okay, so if there's nothing written next to the clock transition, that's called unconditional. That, you know, this state diagram would tell us that this counter is going to go through its sequence and it's just going to proceed on every clock edge. Like there's no condition other than a clock edge for it to proceed in its sequence. Now, we're gonna add a condition coming up, but that's what we have so far. You had a question?
So STA would be the external input.
No, STA is just a label. Yeah, I haven't shown any external inputs because if there was an external input, it would go out here. Now, we're going to do that. 'Cause
Okay.
yeah, I'm gonna slowly make this more complicated. This is the binary for that. Yeah, and again, I just chose to do it that way. You know, I could have very easily just put in my legend a base 10 number, like I could have just said base 10 or something, and I could have put 2, 0, okay? See, that's the importance of a legend, right? Because the legend tells whoever didn't make it, you know, what the format of the diagram is. So yeah, when you turn in a state diagram, okay, and the activity is going to be a state diagram, but part of your final project, both the individual and the team, is you have to provide a state diagram. You know, that's one thing that's different with the final project, you know, what you turn in compared to what you've been doing for the labs. The final project, what you submit, there's more than what was asked for the labs. And I'll talk about that more when we get closer. But anyway, I just mentioned that right off the beginning because that's a common thing that happens is people turn in their final projects. You know, they got their FSMs all working, you know, and they show me the code and everything else, but they don't include a state diagram. And I'm like, you know, that's where you have to start. So anyway, okay, but any more questions up to this point? Like I said, we're gonna add some more stuff here, but this is like the most basic of a state diagram. Okay. All right. So the next thing I'm gonna add is I'm gonna add an external input. And I'm gonna add external input enable. Okay, which is active high. And this enable input, if it's active, it's going to allow us to continue in the sequence. If it's not active, we're just going to stay at the state that we're presently at, Okay. So, for example, in state A, if the enable is high, we're going to go to state B, right? If we're in state B, and the enable is high, we're going to go to state C. If we're in state C, and the enable is high, we're going to go to state B. If we're in state B and the enable is high, we're going to go to state E. And if we're in state B and the enable is high, we're going to go back to state A. Now, again, remember these arrows represent clock transitions. So this implies that enable is synchronous, right? So it's when enable is high and we have the clock edge, that's when the transition happens, okay? Now, if the enable is not high, to show that we're just going to stay in the same state, well, now you have another arrow that shows the clock transition, and you would just put, you know, like not EN, right? Because if EN is 1, not EN is 0. Okay, so we just stay this. Okay, so you see EN would be an external signal that just determines whether we're going to continue in the sequence or not. And if we're not going to continue in the sequence, we just stay where we're at. Okay, so anybody have a question about that? Does that make sense? Okay, we're also going to add a reset input because often you'll have a reset, any sort of FSM design. And in the legend, you would actually show the reset as a separate like a separate entity. And we're going to make the reset asynchronous. Okay, but whether the reset was asynchronous or synchronous, it would be shown the same way. The only reason I'm showing asynchronous is because I want to show you something in the code that you haven't seen before. Like you haven't seen how to make an asynchronous input yet in System Verilog. But let me just say that typically resets are not synchronous, okay, or asynchronous. Typically resets are synchronous, okay? I'm only doing this for an academic, okay? But like I said, that's how you would show it in the in the state diagram. It's just like a separate input going into the bubble like I've just drawn. Now, in the state diagram, I'm just gonna choose that if reset is active here, high, we're just gonna go to state A. All right, I'm just choosing that by random. I mean, you know, maybe you do a state diagram like this and you want to go to some other state when it's reset. I'm making it go to state. Okay, so the next thing we're gonna do, again, just to make it a little bit more complicated, is we're gonna add a mealy output. And the mealy output we're gonna add, actually, I forget to write up here, but now that we know that we had an external output EN, you'd have an EN. Right, so that's our external input. So in our ledger, we put EN. Okay, so I'm gonna add a mealy output, and the mealy output I'm going to add is an LED. And I just decided that in my design, I want that LED to light when the sequence starts, and I want it to light when the sequence ends. Otherwise, I just want it to be off. Okay, so since I'm making a mealy, the LED would go here. Just gonna call it LED. So when the sequence starts, I want the LED to be on. So I would show it like that, a slash and then LED. And then when the sequence ends, I also want the LED to be on. Otherwise, I want it to be off. So, you know, if we're in state A and we stay in state A, I want the LED off. Right, we're in state B, we stay in state B. I want the LED off. If we go B to C, I want it off. You know, I want it off everywhere else. And that's just how I decided to do the design. You know, if you decided to keep it on at some other place, you wouldn't put the not LED. You guys got them all, right? Not LED there, not LED. Did I miss any? Not LED, not LED, not LED, not LED, not LED, not LED. So you see, I'm only lighting the LED when the sequence starts and when it ends. Okay. So anyway, this example, it shows all the things that we talked about, right? It shows the states. We have a state for each of the numbers in our sequence. It shows the more outputs. Again, the reason why you put more outputs within the circle is because the circle represents a state, and the more output only depends on the state you're in. Okay, the mealy depends on not only the state, but also an external input. So you see, that's why the LED is a mealy output, right? Because it not only depends on the state, but it depends on this enable external input. Okay. So any questions about the state diagram? Because the next thing to do, well, also we need one other thing. Let's do one other thing, then we'll take a break. And then when you come back from the break, I'll show you the system Verilog you need in order to actually model this FSM. But before we take the break, let's show what the high level black box diagram for this counter FSM would be. Like, what inputs do we have here? Got reset table. We got reset. Data. Well, what did you say after reset? You said reset, and you put something else. Enable. Clock. Yeah, clock is the other one. Yeah, there's no data input. Yeah. All right, so those are our inputs. How about our outputs?
Right. Right.
Say that again.
Right.
Right. Like WR?
Yeah.
Where do you see that?
Bottom.
Yeah, we're looking at this right here.
Oh.
So, you know, enable is an input, reset's an input, and then you got to have clock because the FSM has memory, right? So you're always going to have a clock input to an FSM. But what's our outputs here?
Binary and really.
Yeah, LED in the number, right? So call it count. Am I missing something?
Yes.
So what am I missing? What should I put here?
Oh, like slash three.
Yeah, we need a /3 for the count, right? Remember, it's 3 bits. Okay, so this would be our high level black box diagram for this FSM counter, right? We got a reset input, enable input, a clock input, LED output, and then a 3-bit count output. Okay. All right, so let's take a 5-minute break. So let's say 10 past, and then the last thing we'll do before you can do your activity is I'll show you the system Verilog code you need for this state diagram. Just ask me a question. Yeah. There's no watch back.
The file, you got it out. Okay.
You got that.
It's good, so it's like I can see it.
Turn off this. Just like.
No, don't cut.
Yeah, that's not.
Though, if the butter. Hard. So how? The irony, that's just all that. You know. Whoa, that's not very much. That's leading into shit.
Anyone want to sing like on this week?
Yeah, you just give it and you put. You let me be 30. The 7-second footer we made. It's representing to see. If anybody, yeah, just as. That's all it is. And we don't choose. One. And the showing that's it for the and the June to even find the wood is the HMR needs this many like one tank very oh yeah and then nice is okay. That's the like in the middle and it's up fine to then it's 57. So if you all, we need to find the cheapest way to cut it. Forgive it or give it. And then what they're like, then you get to make a box. We're just cutting more the. Oh, you just cut it out. It's gonna reply. Like the methods. So I'm thinking. You don't get the things, but I get. That's all. Can you give me a thought? So I'm thinking what are you going to say? Load it.
Okay, so let's go ahead and get started again. So again, I just want to emphasize that anytime you go to design an FSM and you're going to be doing it, let's say again, for lab 6, your individual final project and also your team final project, you always start with the state diagram. Again, I can't tell you how many times I'll have somebody come to me and they're having problems with, one of those labs or their final project. And I ask them, I say, well, can you show me your state diagram? And they'll go, wait a minute, let me write it down. Right, because they're trying to do everything in their head, and or 9 out of 10 times, once they write it down, they're like, oh, that's what I'm not doing right, So don't try to keep it all in your head. Okay, so we're gonna go ahead now and we're gonna model this FSM. And you're gonna see that the code that you have to use to model the FSM, it comes directly from the state diagram. Okay. So first, you start off like any module, name, and you got to declare your inputs and outputs. So again, you would just go to your high-level black box diagram for your FSM. There's your inputs and outputs, and you know all how to do that now. Okay. The next thing you would do that you haven't seen before is that you have to declare the states, like the states in your state diagram. Now, there's a couple of different ways that you can do this, and if you look at the activity that you have, right? So I put an activity for each person on the table. Okay, if you look at the activity, in between where the output is declared, the output D1, D2, in between where that output is declared and where the always FF begins, you see where it says parameter, then in square brackets 1 to 0, and then it has like state A, state B, and state C, and so on. Then it has internal signals, NS that stands for next state, and PS that stands for present state. That's one way you can do it. Okay. I don't particularly like this way, and I'll tell you why after I show you mine. All right. So even though what I'm about to show you is different than what's on the activity, it does the same thing. Okay, it's just what I'm going to show you is more convenient, and I'll explain why it's more convenient once I write it. Okay, so instead of what you see on your activity, what's better to do is to put type EEL, right? So it's short for type definition, and then ENUM, which is short for enumeration. And then in braces, you're just going to put the names, the labels of your states. So since I called my states STA, STB, and so on, that's what I put next. Now, if you call your state something different, you would put whatever you name your states. Because again, this is just a label. It can be anything. Okay. So I'm just going to list my labels for my state. So STA, and then comma, STB, comma, and you would just, put all your states, right? STC, STD, STD, and then you close the braces, and then you put states, semicolon, and then on the next line you put states, PS that stands for present state, and then NS that stands for next state, and then semicolon. Okay, so these 2 lines that I just wrote, they do the same thing as what you see on the activity that's in those 3 lines between the output that's declared in the beginning of the always FF. And you see the reason I like this way instead of what's on the activity, which is kind of like the old way, is that if you look at what's on the activity, each state is given a binary number. Right, like state A is assigned binary number 0, and state E binary 1, and so on. And depending on the number of states you have, that determines how many bits. Right, like if you have 6 states, or if you have 5 states like we have in this state diagram, well, you can't just use 2 bits, right? Because 2 bits can only represent 4 things. Right, so if you have 5 states like we have here, we would have to put our binary numbers for each state as 3 bits. Well, the reason I don't like that way of declaring the states is because if you go in and start editing your state diagram, like say you find out you have to add some states, well, now you got to go back and you got to renumber all those states. And especially when you get to more complex designs, more complex state diagrams, more states, it can be a pain, right? Because it's very easy to like duplicate states or, just mess up. Where if you use this way, this enumeration way of declaring the states, if you have to add states, the software will figure out what the binary numbers have to be. So the software does that work for you. Okay, so that's why this is a better way, in my opinion, to do it. It's especially a better way when you take CP 233. Okay, because again, in that class, you're likely to do a lot of editing to your FSM until you get it working right. So, okay, so after that, this is what the code would look like. Now, when we just did, good question.
What are the states you guys said?
Say that again, please.
States you guys said.
Oh, this stands for present state and this stands for next state. And you're gonna see why we need that coming. But yeah, that's what they stand for, present state and next state. Okay. All right, so when we just did a register or a flip-flop, what kind of always did we have? What kind of always block for sequential? Always FF. And when we did a combinational, we had a what? An always comb. Well, doesn't it make sense that since an FSM has both sequential and combinational circuitry, that the Verilog code that models it would have an always FF and an always comb, right? Because we need the always FF for the sequential part of the FSM, and we need the always comb for the combinational part of the FSM. Right? Doesn't it make sense? Okay, so when we're modeling an FSM, we start with the always FF, right? So we have always underscore FF, and then the at symbol. I have a hard time making an at symbol. That's an at symbol. Okay, and then parentheses. What are we going to put in parentheses if we want this to be rising edge? Pause edge, pause, right? So put pause edge. So that's going to make anything that is synchronous to the clock, synchronous on the 0 to 1 transition. Now, this is something new. And this is why I made the reset asynchronous instead of synchronous, even though, as I said before, resets are hardly ever, if never, asynchronous. They're always synchronous. And you'll learn the reason why in CP 233. Is that what you're going to ask?
Yeah.
Well, real quick, the reason is, like in a microprocessor in CP 233, where you have a bunch of stuff, like a bunch of modules that you want to reset them at the same exact time. If you have something that's asynchronous, the chances of them resetting exactly at the same time is less probable than if you make it synchronous. Because if they're synchronous, they're all in step with each other because they're all, obeying the same clock edge. Okay. So I just wanted to emphasize that because when you take CP 233, don't tell your CP 233 professor that Perk said resets are asynchronous because he used it in an example. Okay, again, I'm only making this asynchronous here as an academic exercise because I want to show you how to do it in the code, but this would be synchronous otherwise. So just want to put that out there. All right, so the next thing we would put, because we want an asynchronous reset, is we would put neg edge and then RST, okay, for a reset. That's what I named the reset with RST. Now, I'll explain in a minute how this makes it asynchronous, but that's what you need. All right, then we're going to have a begin. And I'm going to have if reset is low. Okay, so I think I didn't put that over here. I should have. That we're going to make this an async active low reset. So we need the bar over it. Sorry, I forgot to put that earlier. Yeah, I wanted to make it active low again to show you something I haven't. I think I talked about this, but I didn't show you in a previous class that if you have an active low input in the code, in the parentheses for an if statement, you would put an exclamation point. So that means not reset or, active low reset.
We saw there's a positive syntax for system Verilog and language.
I'm gonna explain this coming up. Yeah, let me just finish this and I'll go back to this and I'll explain it. Okay, so if our reset is low, we want present state to be assigned. And remember, we're within an always FF. So when we assign, we have to use the less than with the equal, like we talked about before. I want present state to be state A, right? Look at my timing diagram. Need the bar here again. Right, so when reset is active with the low, I want to go to state A. So I want my present state to be state A. Okay, else I want present state to be assigned to next state. And then I got to ends. Okay, so let me explain a few things here. Okay, so first of all, is it clear that when reset's active, and again, it's an active low, so that's why I put the exclamation point here. Based on our timing diagram, we just want to go to state A. So this is the Verilog code that does that, right? It assigns present state to state A. If I'm not resetting, well, then I just want to determine my present state, or assign my present state to next state. And next state's going to be determined by code that we're going to write in just a minute, because the next state is determined by combinational circuitry. Okay, so you're going to see that the next state is going to be determined by an always home block, right? Because the always home block is what models the combinational circuitry.
How is the exclamation mark like the squiggly line?
Yeah, great question. Yeah, the way system Verilog is, the tilde, you use that when it's in a Boolean expression. It's called a bitwise symbol because, Boolean expressions sort of are closer to the bits. But when you're in an if statement or a case statement, it's not the tilde, it's the exclamation point instead. So that's the only thing that distinguishes. Like when you're doing a Boolean expression in system Verilog, you do the not with the tilde. But if you're within like an if statement or a case statement, use the exclamation point. Sorry. Yeah, it's just a Verilog thing.
And then also is that so less than equals, or like what is the middle there?
Yeah, this is a less than followed by an equal. So it's the same as in lab 5, right? When you do your D flip-flop and you do your register, you have to use this instead of the equal sign. Anything within an always FF, any output is assigned like this instead of the equal. We just use the equal within an always cone.
So that doesn't mean less than or equal, that means equal.
No, it just means a sign. Yeah, this means a sign. Yeah. Okay. All right. So now let me explain how this neg edge RST makes it asynchronous. Well, you have to go back and recall that anything within the parentheses, that's when this if statement's going to be evaluated, right? Anything within the parentheses, that's when anything within the always FF is evaluated. So if I only had pause edge clock, this code here would only be evaluated on this rising edge of the clock. So that would make the reset synchronous. But now by including this is going to be evaluated not only on every positive edge of the clock, but also any negative edge of RST, right? So if RST goes low, it gets evaluated and the reset will happen.
Is that more like semi-asynchronous? Because if you were to have that reset switch after the negative edge or the positive edge,
Okay, say that again. If the reset
went low after the negative edge or the positive edge, it would.
Well, I mean, you're right that, let's see, because you get there's a delay between the positive edge and the negative edge. So you're right that, there could be like a time. See, if that was an issue, I guess the answer to your question would depend on whether it would be a problem or not, the specific design. Like, remember, we're dealing with 10 nanosecond period, right? So, you're right, there's a delay of what, 5 nanoseconds between each of the edges, the positive, negative edges. So I suppose there could be a case where that amount of time could be a problem, but I think in most cases, you know, who's going to care about 5 nanoseconds? But if it was a problem, if you made them both positive edge, and you know, if the reset's going high the same time the clock edge is, because the reset comes first in the if statement, then it would solve that problem. You know, if the 5-second delay was a problem in the first place. But you are right, there is a delay between the two, and it's possible that could cause an issue. Yeah, you probably have to be a very time critical type of thing for anything we do when it comes. Yeah, that's a good point. Okay, any other questions up to this point? Okay, so questions.
Also like that executes the clock is positive edge, so it's negative edge, like it's zero.
Well, whatever you put within the parentheses, that's when whatever's within the always FF is going to be evaluated. So this is always going to be evaluated on the positive edge of clock and also on the negative edge of reset. Now, if reset doesn't go low, right? You know, this won't happen. I mean, reset's got to go low for this to happen.
So it's either or.
What do you mean by
Like if like positive edge, that'll happen. Or like it doesn't have to be both of them for that future.
Well, if both of them happen, the reset would occur because the reset has higher priority because it's happening, before the else, right? Because remember, like when you did the D flip flop in the if statement, we had the reset first, then the set second, and then the load. So if they're all happening at the same time, reset would have the priority, so that would occur. And it's the same thing here. Yeah, that's a good question. Let's see what I was going to say. Okay, so for an FSM, this is as complicated as the always FF is. You know, when you take CP233 and you model that control unit FSM in 233, the always FF for that FSM is going to look just like this. It's just going to have an if statement. You know, if reset happens, you're going to go wherever you want it to go, you know, for the reset. Else, your present state is going to be assigned next state, and next state is going to be determined by the combinational circuit. So when you're modeling an FSM in Verilog, like the system Verilog, it's the always comb block that tends to be the longest. Okay, the reason I mention that is sometimes I feel as though students think this is too simple, and they try putting stuff that goes in the always comb, they try putting it here. Like they feel like, oh, it's got to be more complicated, but this is all your always FF is going to be. Okay. All right. So now comes the always comb. Always comb. We need to begin. Okay. So what I chose to do here, and I think I mentioned this before, is I chose to initialize all my outputs first before I start into a case statement. I used the case statement for what you're about to see next. I mean, I couldn't have used an if, but I decided to use case. And I think most people, when they do the always comb, you know, they use a case statement. And again, the reason I did that is because if you initialize all your outputs at the beginning, then you really only have to list the outputs that change within like a case statement or an if statement, as opposed to, you know, all of them if you don't initialize them. So that's what I do first, is I initialize. This is in the way. Let me move this. So, you know, if stuff is in the way, let me know. Or you can move it too. Like if you're too far back and you want to come up front so you can see here, you're more than welcome to. Okay, so what I did here is I initialize count to 0. So since it's 3 bits, 3, tick mark B, 0, 0, 0. And let's see, that's a semicolon. And then LED, I just assign to 0. All right, so this is just initializing outputs. Initialize outputs. Okay, then I'm going to use a case statement. All right, so case. And I'm gonna make the case statement sensitive to present state. Right, because whatever you put in the parentheses, when that changes, that's when the case gets evaluated. So you see, if I'm not resetting, present state is gonna be assigned next state. So that's the change, right? So like once this hits the else, it will go to the combinational circuitry to find out what the next state's gonna be. Okay? All right, so let's see. Let's come up here. Running out of space on the bottom. We'll come up over here. Let's see, am I still in view? Yep, all right, good. All right, so now I'm gonna go ahead and do the case statement, right? The different options. So I'm just looking at my state diagram. One option is state A, right? So I put state A, colon, in, and I look, and state A has an output of 2. So you always put the more output first, because the more output only depends on the state you're in. So once we're in state A, we know the more output is this. Okay, my more output is my count. Right, so I just put count equal to 3, tick mark B 0 1 0. Okay, so you see this is the more output. Okay, now comes the mealy, right? In the mealy, not only depends on the state you're in, but it depends on an external input. Right, because when we're in state A, if this external input is high, we're going to go to state B. But if that external input is low, we're going to stay in state A. So we're going to need an if statement for that mealy output. That an if statement that's conditional on enable, the enable input. So you see, that's what comes next, is I'll have an if statement. Okay, so here's your first example of an if that's nested within a case. Okay, so we put the if statement. So if enable is high, got to begin here. We're going to set LED to 1, semicolon, and we want to set LED to 1 if enable is high. Also, we want to go to state B. So LED equal to 1 and next state equals state D. And then I end this. Right, so this is what happens if enable is high, right? I want to set the LED to 1 and I want to go to state B. Else, right, if enable is not high, right? I want to make LED equal, oops. I want to make LED equal to 0. And I want next state to just equal the state I'm in, right? Which is state A. And then I would end this. And let's see, do I need another? Yeah, this end goes with this begin. Then I got to end the state, so I need another. All right, remember, you got to have an end for each begin. So this end goes with this begin, and this end goes with this begin. I always got to check that because that's a common mistake I make, because I always end up not having my begins and my ends match up. Okay, so let's just take a moment. I mean, any questions up to this point? Do you see how what I wrote right here? I'm just looking right here. I'm just looking at my state diagram. I'm saying, okay, when I'm in state A, the count is 2, that's a more output, that always goes first, right? Now I take care of the mealy. The mealy depends on the enable input, so it's an if statement, right? So here's what's gonna happen if the enable is high. Here's what's gonna happen if enable is low, right? And I'm just looking at my state diagram. That's probably the key thing of this, is just being able to translate from the state diagram to the code. Okay, all right, well, if that made sense to you, it's just repetitive from here on out. All right, let's do state B. State B, begin. Okay, what's my count in state B? All zeros. So 3, tick mark. Oops, I forgot the B. All right, B, all zeros. Again, that's my more output. That's the more. Okay, if enable in. Okay, I'm looking right here. Right, state B. If enable, if I have enable, I want the LED to be off. This is a line. Right. Remember, we only wanted the LED on when we began the sequence and we ended the sequence. So this would be LED equal to 0. Okay, but I will go to next state. I will go to state C. And then I would end that. Else. Again. Else LED is going to be off, and I just stay in state B. Right, so LED off. And next state in state B. Right, and then I would just end that, right? And so we need 2 lines. Right, so do you see how I'm just doing the same thing as I did for state A, right? I'm just looking at state B and saying, okay, that's my more output, that comes first. Okay, enable is high. I go to state C and I have the LED off. Right, else I'm just going to stay in state B with the LED off. And you would just, for the rest of this, you would just continue on. I mean, are you confident that you could do state C, state D, state E, right? It's going to be the same process. You have a question?
If you initialize LED to 0, do you have to assign it 0 later on in the block?
That's it. Yeah, we initialized it to 0 here. Oh, so you're saying right here, if we even need this.
Right.
Let's see, because we set it to 1 here.
Or even just like in the state case.
Say that again.
In the case of state B, for example, if the LED is going to be off regardless, do we have to assign it 0?
I don't believe you do. The only reason I hesitated here is because we set it, let's see if it was set, well, it's set to 1 if the enable. Yeah, so if the enable is high. So let's say enable's high here and you get to this state that's on, but then like enable goes off and we stay there. See, I'm not sure, to tell you the truth, is that if the enable was high during this transition, so the LED lit, but then the enable goes low, if not having this would cause it to go low, like I think you would need it to make it go low, otherwise it would stay high. But the thing is that in what we're doing here at the frequency we're dealing with, you probably would never run into that. You know, you might run into it if the frequency was lower. So I think the answer to your question is it depends. Like the answer to most good questions, I think it depends. Now, I think, you know, however, I do think that, you know, this is really cookie cutter. You know what I mean? Like, if you just follow this format, you're not going to run into a mistake. Now, if you pick some shortcuts, I mean, the advantage there is you save some code, you know, but you could run into a problem depending on the particular situation. So, right. Was there another question?
Is safe like or limiting our safe issue? Like for the transitions, like in that piece where we have the legal LED non for like I think like 4 of the transitions. Is there a way to like create like a function like that?
Oh, in the code? I don't doubt that there is, because you know, System Verilog is based off of C programming, and I know you can do functions like in C, so there's probably you can. Now, have I ever done it? I haven't. I don't know of any other instructors that have, but that's something where, I mean, there's lots of information online about Verilog. Now, there's not so much information about System Verilog, but the thing is, like I've mentioned in previous classes, there's not that much difference between Verilog and System Verilog. So if you Googled it, and if it can be done in Verilog, it can be done in System Verilog. Because System Verilog can do what Verilog does and some more. Yeah, no, that's a good question. Yeah, I'm not sure. I haven't tried it, but yeah, I would think so. Like I said, because it's based on C. Okay, let's see. Let me just. Oh, so you would just keep going, right, for the other states, but then remember, this is a case statement, right? You know, these ifs are within a case statement. So how do you end a case statement? Like, what do you have to have, like, after all your options? A default. So, you know, you would go, you know, here you'd have like your ends for state E, you know, that last state. You know, state E would be up here. Right. That I'm guessing you could fill in all of this. But then you would need a default for the case statement. And I just made the default next state assigned to state A. Okay, and then you'd have to end the case. And you'd have to end the always home block. Right, so this ends the always home. And then you'd have end module. Yeah, one of the most difficult things I think is just making sure you have all the ends that you need. Because like I said, I know when I do this, that's a common thing. Like I'll miss like an end case or an end or something, and it's, yeah, you just gotta match them up. That's where, oh, that reminds me, you know, there's like software, like programs online that are free that will like color code your code. You know about that? Some of you know about it. Really handy. Yeah, like when you do your final project, because your final project, I do require that you turn in the code. That's something that I really would appreciate it if you do that. And then when you take CP 233, there are instructors, and I'm going to start doing this next quarter, that require that you use software like that where color codes. It just makes it so much easier to read, and it's so much less likely that you'll make errors like I was talking about. You have a question? Yes. Yeah, and you see that's bad because the always comb is representing your next state decoder. And so what would happen is it would put like a latch in the circuitry. Now, again, sometimes if you have an unintended latch, sometimes your design will still work. Now, it won't be as efficient because when you add a latch, that's adding circuitry like the logic circuitry that we looked at prior. So it's going to slow your, you know, process time down some. But, you know, if you don't have something that's time critical, it might still work. But again, the reason why we really work on that, you know, during this class is because in 233, again, that microprocessor, if you have unintended latches in that, it's not going to work. Or it may work sometimes and not other times. It might work with some instructions, but not all instructions. Yeah, unintended latches are something you don't want to deal with. All right, are there any other questions? Oh, no.
How does it like, yeah, create a latch?
Well, it's just that Verilog, the way it's designed, that's how latches are formed, by either leaving out an else in an if statement or like a default in a case statement. Now, there's other things that will cause it too, but those are the two things that people will do to intentionally make a latch, right? Like if, you know, because I talked about how you leave out the else, but you know, if you had a case statement within always FF and you wanted to create like a storage, you could leave out the defaults. That's another way to do it. Yeah, I mean, that's all I can say. I don't know why they decided to do it that way. That's how it's done. That's how it's modeled in the code. Any other questions? Really good questions today. Good. Okay, I know I went long today. I'm just trying to think. We got 2 more lectures, so there's one Tuesday. I was going to tell you about this next week, but I'll tell you now. We're not going to have class a week from today. I actually have a medical procedure I have to go to. But that's okay because as far as the content that's covered, you're not going to miss anything because we actually had an added class this quarter because we started on a Thursday. So even though we're going to miss next Thursday, I'm still going to cover everything that I normally cover. So I don't want you to think you're getting cheated out of anything, but anyway.
So we have more lectures.
Well, 2 more in-person lectures. There'll be one Tuesday of next week and there'll be one Tuesday a week after. Like I said, a week from today, I won't be here. And then there's an open lab, before Thanksgiving break, that's an open lab. And then when you come back from Thanksgiving break, there's no more in-person because that's time for you to work on your final project. And that's when I'm available on Zoom as you're doing that. Now I'll talk about the final project the Tuesday before Thanksgiving break. So, yeah. All right, any other questions? So the thing to do now is to work on that activity. The activity is you're given the code for an FSM and you're to draw the state diagram. So, I went from state diagram to the code. The activity is going from the code to the state diagram, right? It's going the other direction. Okay.